Hi everybody! So today's video is going to be about something called the mean value theorem, which is the second of two major theorems that we're going to be learning this year. So I want to review some vocabulary with you because this vocabulary is necessary in order to understand the meaning behind this theorem. The first thing I want to review for you is that in math, the word mean has a very special meaning. The word mean in math means average. So a mean value theorem, and the reason we call it this is because this theorem compares the average rate of change with the instantaneous rate of change. Just to review with you, the average rate of change is f of b minus f of a all over b minus a. And the instantaneous rate of change is f prime, or the derivative. So here's what the mean value theorem says. The conditions are the ifs. That means we need to check both of these boxes before we're allowed to apply this theorem. If f of x is continuous on the closed interval that we are looking at, which means the endpoints need to be included. And if f of x is differentiable on the open interval, meaning we don't really care about the endpoints, then, so the conclusion we can make, the then, is this. On that interval from A to B, the average slope, which is f of b minus f of a all over b minus a, must be equal to the instantaneous rate of change, which is the derivative, for some specific x value. Which is why we write c instead of x. We use this when we are trying to guarantee that a function has a certain slope. We also use this when we are trying to locate the specific place where a function's average rate of change is the same as its instantaneous rate of change. Instantaneous, there we go, I can spell. Now, if we were to look at this visually, here's what we're really thinking about. If we imagine some sort of a curvy function, and we choose two random points, so we're going to call these our endpoints, here and here. If you were to look at the average rate of change, or in other words, the slope of the secant line between those 2 points, what this theorem says is that the slope of the tangent line must be the same as that slope at least one time within that interval. In this example, there would be 2 places where the tangent line would have the same slope, and we can tell because they're all parallel. All that this theorem allows us to do is find the place where the slope is the same as the average slope. So let's take a look at the follow-up questions. The first question asks us to determine whether these functions do or do not satisfy the conditions of the mean value theorem. If they do not, we need to explain why not. So the first thing we need to do is check to see if we are continuous on the closed interval. In this case, since this first point right here is not connected, we are not continuous on the closed interval. So the answer would be that no, we're not continuous on that closed interval. we don't even have to think about whether we're differentiable or not because we didn't pass the first test of being continuous. For part B, the first thing I'm going to ask myself is, are we continuous on the closed interval? In this example, yes, we are continuous on this closed interval. Then I would move on to part 2, which is, are we differentiable? On the open interval, meaning we don't really care about the endpoints. Since this function has a corner or cusp, it's hard to tell from this graph which one that is, at this first x value, we would say no, we're not differentiable. For part C, it says we would check first, are we continuous? On the closed interval. Well, yes, we are continuous. The endpoints are included, everything is connected. The second question I would ask myself is, are we differentiable on the open interval? Meaning, is everything nice and smooth? There's no corners, cusps, vertical tangents, or anything like that. From this graph, I would say yes, we are differentiable. There's no corners, cusps, vertical tangents, or discontinuities within our interval. Finally, for part D, I would ask myself, number 1, are we continuous on the closed interval? In this problem, I would say no, because there's a vertical asymptote, which means I'm disconnected. There's an infinite discontinuity within this interval. Because I'm not continuous, I'm not even going to worry about whether I'm differentiable or not. The next follow-up question, we're going to kind of take it a little bit further. So after we've decided in this question whether we meet the conditions or not, we're going to actually practice applying the theorem. So applying the mean value theorem to g of x on this interval guarantees that there must exist some value such that the derivative is equal to what? So we're trying to figure out, what slope can you promise me? Well, what the mean value theorem says is that I can promise you your derivative is equal to your average rate of change. So in other words, I can promise you that this slope is equal to g of 2 minus g of 0 over 2 minus 0, because those are the endpoints of my interval. Let's see here. To calculate this, to actually figure out what slope you can promise, I'm going to take the 2 and plug it in. So I get 12 plus 4, which is 16, plus 1, which is 17, minus, if I plug in 0, I just get 1 over 2. That gives me 16 over 2, which is 8. This problem does not ask me to figure out the exact x value where I achieve this slope. It doesn't say find c. It just says, what slope can you promise? Well, I can promise this slope. So that's my answer. Last but not least, it says, given this equation on the closed interval, first, what is the value of f prime that is guaranteed? So again, this is saying, what slope can you promise me? To figure out the answer to part A, we're going to do the same thing we did in the previous example, which is to find the average slope, because I can promise you that the derivative, which is the instantaneous slope, is equal to the average slope using the mean value theorem. So f of 3 minus f of 0 over 3 minus 0. If I plug in the number 3, I get negative 2 cubed, which is negative 8, minus if I plug in 0, I get 1 cubed, which is just 1, over 3. So I get negative 9 over 3, which is negative 3. So I can promise that f prime is equal to negative 3 at least one time. what is the value of C that satisfies this conclusion? Part B is a little bit different than Part A because Part B says, now find the value of C. So this is asking me, where does f prime of x equal the slope that I just found, -3? So let's see if we can figure that out. In order to do this, the first thing I'm going to need to do is find f prime. So taking the derivative of this function, I get 3 parentheses 1 minus x squared times the chain, which is -1. So my simplified derivative would be -3 times 1 minus x squared. After I have the derivative, I want to find the specific value that I could plug in here that would make my derivative equal to -3. So the way that I set up this part is I say, instead of using x here, I'm going to replace the x with c because that's the value I'm looking for. So -3 times 1 minus c squared, and I want to be equal to the value -3. I want to know where the slope equals -3. So where specifically does this happen? If I solve this equation, I'm going to divide by -3 first, so I'm going to have 1 minus c squared equals 1. I'm going to square root both sides, so 1 minus c equals plus or minus 1. I'm going to solve this by saying -c equals -1 plus or minus 1. And that is really two separate answers. -1 plus 1 would be 0, and -1 minus 1 would be -2. Last but not least, I'm going to divide by my negative. So c equals either 0, because -0 is just 0, or 2, because -2 divided by a negative would make positive. Now you might be wondering, can I have two answers? The answer is no. The answer that we find needs to be within this interval. Since 0 is one of the endpoints and not between those two numbers, only the 2 would be my answer for this problem. Thank you guys so much for watching, and I will see you in class tomorrow for some practice problems.